and it falls into what we call the thyristor category. And what does SCR stand for? And what makes it different than a regular rectifier diode? Yeah, that's the way it's constructed. What makes it different? Yeah, so what we have to do with this guy, we have to turn it on. We have to meet up two things. We have to forward bias it. Let me turn on the projector, yeah. So, first of all, as soon as it comes up, we have to forward bias it. And let me move this down a bit so I can show you the little circuit I have hooked up there. Very, very simple. So start off with the same basic symbol as a diode. Then what we do is we come over here and we put another lead into this thing. And of course, what do we call this lead right here? What? Right here. Yeah, we call this the anode. And what do we call this lead right here? And this lead right here, we call it the gate, right? So what makes this different? So to forward bias it, we have to make the anode positive and cathode. But that doesn't make it conduct. What do we have to do? What? Yeah, the gate has to be positive in respect to the cathode. So if we made this, I'm not going to put negative. This is in respect to, everybody understand that. And this would be positive. But what we have to do is we have to forward bias the gate to cathode. So that means I would put a positive pulse here and then this guy turns on. So that's why it's called a silicon control rectifier. So we control when it turns on. Now once it's on, how do we turn it off? So let's say I come up here and take that away. Will it turn off? No, what turns it off? Huh? We have to drop it below its current holding current. I think I showed you a circuit, and there's a circuit in the book where we put this guy on DC. And if we put it on DC, we can't really reverse bias it, right? So y'all understand. So what we do to turn it off is we drop it below its what? Its holding current. As soon as we drop it below, now reverse biasing it will do that. Y'all understand that? So the circuit I have hooked up here is a real simple circuit. This is a pretty common circuit. And what I'm doing is I'm controlling the speed of the motor. And I can get time to play around with it long enough to... So what I've done is I've took the armature of the DC motor, which is the rotating part. And this is the symbol we use for the armature. And then I have this hooked up to a transformer. So I start off, I got a transformer. And it's a center tap transformer, but I'm not using the center tap on this circuit. So what I'm doing is I've set up one circuit as being this side to be in my common. And then what I've done is I brought this over, and then I'm running it through a resistor. And then I'm running it through a pot, or it's a pot wired as a rheostat. And then I have a capacitor. So I've set up a little RC, what we refer to as an RC time constant. And I don't know if y'all remember this, but all y'all have had AC, but time is equal to R times C, right? Close to it anyway. So what I'm doing, then I'm taking right here and I'm bringing this over and I'm hooking this up to my gate. Then I have this connected to common. And then I have my armature of my motor up right here. On DC, the armature is the part of the motor that rotates. And then this is a permanent magnet motor, so it doesn't have a electromagnetic field. So it's a permanent magnet motor, and the permanent magnets are out here. So when I put power on this thing, it should rotate. Now, DC motors, they had the advantage for years as being very easy to control. AC motors are real hard to control the speed. For one thing, we're putting AC on them. So, and the motor rotates, on an AC motor, the motor tries to rotate. It never hits this for reasons we know. It's 120 times the frequency divided by the number of magnetic poles that we have. So what happens on an AC motor is that if you reduce the voltage to it, it doesn't produce the horsepower and it will stop. If you put too much voltage on it, then it's going to burn up. And of course, if the motor stalls and we don't protect it, it don't burn it up. So what we do with an AC motor, we got two options. We can change the number of poles. And magnetic poles, of course, come in north and south, right? You understand? So that means if I come over here and had a rotor, and then I had only a north and a south, of course, this can be swapping, then that would be a two-pole motor. 120 times the frequency divided by the number of poles means this motor would try to run at 3,600 RPM. If I went to two more poles, and I'll set them right here, then this would be a four-pole motor, and it would run at 1,800 RPM. And this is why, if you got a ceiling fan, that's what you're doing when you're flipping that switch. If you look it up, it's got 4 wires, 3 wires coming out, and what are you doing? Well, every time you switch it, you're changing the number of what? Poles. And that's the way they work. And a lot of motors work like that. The motors in your air conditioner is usually a 3-speed motor, and what they're doing is changing the number of poles. But the speeds would be set. So that means, okay, if I want to change the speed, then if I want to change it electronically, then we're going to play around with the frequency, right? You understand that? But the problem is, in AC, we learned a formula where X of L is equal to 2 pi FL. Well, see, now we got two problems. If I lower the frequency down, the X of L does what? Goes down. And now the motor's going to pull more current. If I raise the frequency up, then now my X of L goes up and the motors may stall. So AC motors, we don't control it with the frequency by itself. So what we do is we set up what we call a voltage to hertz ratio. So if I raise the frequency, I raise the voltage by the same percentage, right? You understand? And if I lower the frequency, I lower the voltage. So that's why for years and years and years, if we wanted to control the speed of a motor, they were DC motors. Because a DC motor, we could control those with SCRs, right? Very, very easy. But electronics came out. Now we have variable speed drives, and that's what the variable speed drives. Now the advantage of AC motors, they're a lot cheaper per horsepower. And if you're going to control the speed of the motor, you're going to have a drive anyway. So this is why in our speed controls on new applications, AC motors are dominating now. But for years and years and years, we had DC motors, and they're still out there. And there's some applications you can't put AC motors in, right? You'll understand that. So this little SCR circuit, what we're doing is we have the armature, we have a permanent magnet motor, and what I'm doing is I'm delaying the firing of the SCR. And if I delay the firing of the SCR, then what we're doing is we're turning it on later in the cycle, right? And of course, we looked at this, but it's half wave. So what we're actually getting on this, if we turn it wide open, then what we would get across the motor is we would get this, right? You understand? And then if I delay it with that capacitor, then what I'm doing is I'm letting less of the AC go through. Now this gets hard to look at with an oscilloscope. So if I do this, then this is the amount of AC the DC the motor will see, and the motor will slow down. The problem with an oscilloscope, and y'all probably want to come up here, is that an oscilloscope, if I look across the SCR, I'm going to see when the SCR is turned off, right? You understand? So what we'll see across here is we'll see a little hump right here, and then what we'll do is we'll see, then it'll stay off, and then we'll see the whole negative alternation. Well, what actually the motor's seeing, and I'm looking across the SCR. So what I see is when the SCR is turned off, right? You understand? So when it's turned on, and the problem is I can't move my scope probe up here. If I move my scope probe up there, I got a short circuit, right? You understand that? Because a scope probe is ground. Everybody understand that? So when we look at this thing, we're going to have to put our scope right here. So what I'm seeing is I'm seeing when the SCR is turned off. So if I see something like this, it means my motor is actually seeing that. Y'all understand? Okay. Y'all probably want to come up here. I'll put the camera on it. Let y'all come up here next to me. I just screwed up. I pulled my motor completely out, guys. So I want to go to my anode, which is right here. And then I'm going to go back to the positive. Oh, and I lost my ground. Now, all this is motor noise. Okay. So this is where my SCR is actually turned on right here. And this is the best I can do. So now it's seeing this whole alternation. Now it's seeing that whole alternation right there. You guys turn it off a little bit. And this is a pretty fast design, so I can't turn the motor all the way off. I couldn't come up with the right setting. If you can hear it, that's why I got that tape in there flopping against the table. You can hear it what? And the SCR itself don't get hot at all. Why is that? Because it's either off or on. There's no in between. Very simple circuit. Now, when you get into firing circuits, they get very, very complicated because they have to do a lot more. Let me turn. Okay, see how I see that? Pretty neat. And that's a very simple circuit. Very simple. Now, if you this is safe. We're only using 12.6 volts. We don't exceed the breakover voltage of this junction right here. But if you're going to work in a bigger circuit where you're using a higher voltage, then you need to put a diode up here so you wouldn't exceed the breakover voltage of the SCR. Huh? No, you just put it in this line right here. Normally we would come up here and put it right here. So right now I'm only using a 12.6 volt transformer, and we got all this resistor. So we know when we reverse bias a thing. So what's happening is the gate. If I look at the gate, you see where it's clipping when it fires. So this is the gate. So it's still firing even though I don't have it hooked up. Well, see right here is when it actually fires, when it goes positive. Well, if this right here dropped down far enough to exceed the breakover voltage of the SCR, I would just screw up the SCR, right? You understand? If you break over a diode, a PN junction in the reverse direction, except for Zeners, we protect Zeners with big resistors, and they're designed to be reverse biased. This guy here is not. So what I'm saying, if you're dealing with a high enough voltage, once you come through all this stuff, if this voltage right here is high enough to break that thing over into reverse voltage, then you'd come in and you'd just put a diode right there. So what it would do is it would let the positive come through, but when this right here went negative, it would block it. Right? Very simple circuit. Okay, y'all go ahead and sit down. We'll look at some firing circuits to let you see how complicated they are. A lot of them don't give them away because they're very complicated to so these are the ones. This is the basic one that of course, this is the basic one we have, sort of like the one we have right here, except we got a capacitor. This is more like it, but this is the guy called a UJT that we're going to talk a little bit about. A UJT gives out a high energy pulse. Another problem we have is that if my SCR is running extremely high voltage, then we don't want to bring that high voltage into our firing circuit. So what we do is we pulse it through a what we call a firing transformer. So this is an SCR firing transformer right here. So this is one right here. And what it does is a 1 and 2. This is where we would put our firing circuit, and then 3 and 4 is where we would put our SCR. It's got dots on here that gives you the polarizing. So it means if we hook this up right, if this is positive, this side right here would also be positive. So that's what the dot means. Because if you hooked up the secondary backwards, the SCR would never fire. Because it would be negative it would be positive when the SCR is reverse biased. Y'all understand that? Because when you go through a transformer, you get a phase reversal. So what they do, and these are polarizing dots that shows you each one. And this is a 5-to-1, so that means I don't know if it's backwards or not. I don't know if it goes 5-to-1 or get 5 times out more than you put in. I'm not sure. But this is a standard pulse transformer. And what it allows us to do is it allows us to so it allows us to have, you know, over here we might have 2300 volts running our motors. But I don't want to bring that 2300 volts in my cabinet. So what we'll do is we'll come over here and we'll put one of these little pulse transformers out here. And then for my electronic circuit that's firing the SCR, it will run 2 little wires over there, one from the cathode and one from, so we'd have to bring this into it. So these guys here will have multiple wires hooked on. So what they do is on the cathode side, they'll bring another wire over like that, so it won't be a common. Then what we'll do is we'll have our transformer over here, and then this right here will go back to our electronic firing circuit. That makes sense? And then what we'll do is we'll take this AC, and then we'll run it through a transformer, steps way down. And what this does, this allows electronics to be in sync with the voltage going to the SCR. Does that make sense? And then this will be this little pulse transformer. And what they're doing is they put those little dots on there so you know how to hook it up. Because if you hook up you got 2 leads on the output and you hook it up backwards, that means you'd be getting your positive pulse when what? When the SCR was reverse biased. So these are pulse type transformers, and what it allows us to do is to have a low voltage firing circuit controlled at a high voltage circuit. These are isolation. So we used to do SCR labs, and this is we made sure the students understood that. And normally we fire it through a circuit that gives us a high energy pulse instead of trying to do this. So normally we fire it with a device called a UJT or a device called a PUT, which is a programmable UJT, which is becoming very popular. I don't see any more complicated circuits. So these are pretty simple circuits. This is getting a little more complicated. Somebody drew that up. But SCR firing circuits are really hard to come by because people don't want to give away their secrets. So this is this guy called a UJT, a universal unijunction transistor. And the way the thing works is when this gets up to a certain potential, this guy here fires. So it's no gradual thing. It'll fire and put a high energy pulse into the SCR. And then what we would do is we would put our pulse transformer right there if we're going to run a real high voltage. Let's see if they show any of those. So this is a little more complicated right here. No, this don't really show it, but this is the actual sync circuit. This is the circuit that's syncing the AC with this. But here's our 3 SCR, our 4 SCRs right here. Of course, you don't really need 4 SCRs. All you really need is 2. So they get pretty complicated. And like I said, these are trade secrets that a lot of people just don't put out. What do you mean? Are they inside a pack? They could be. I've never seen them. I've always seen them where we have an electronic circuit that controls the firing, and then the SCR is out there somewhere else. Yeah, you have to understand. I worked at US Steel, and we didn't deal with milliamps, or we were dealing with hundreds of amps in the DC motors that we drove. So the SCRs were out there, and they were all heat sinked or water cooled. I think I showed you all the water cooled jacket. We had a unit that was on an induction heater that used the water cooled SCRs in there. They were really cool. All the rest of them were on big old heat sinks. So, water cooled, yeah, big packs. And why they water cool them, of course, because it take those big heat sinks. You get up in there and 600-700 amps, way on up there in those high power. The heat sinks to get the heat away from the SCR, they're going to be huge. Well, if you water cool them, then you got that little thing I showed y'all, right? The water cooled jackets. That would be that, and that would take the place of the SCR. I mean, take the place of the heat sink. And like I said, we had one unit out there that used water cooled jackets. All the rest of them were older, and they all used heat sinks. And you could tell the difference real fast. But see, these are firing circuits, and they become very complicated. And like I said, it's real hard to find schematics on firing circuits because they just don't want to give them away. I wish I could find those out at US Steel. We had all the schematics on all that stuff. We used to fix we used to fix these circuits to the component level, which was pretty neat. So I really learned a lot out there. Yeah, we almost had nothing that left the plant to go out. We didn't see anything off to get fixed. We fixed everything with that. So I learned a lot. You see a lot of them using a UJT, so we need to talk a little bit about that guy, not much. But yeah, so the ones they're actually showing, so these would be the pulse transformers right here. We call these pulse transformers. And then what it allows us, it allows our electronics over here to be what? To be isolated from the SCRs themselves. So the next device we want to look at real quick is in your book. I don't remember a chapter. I can't find my book, guys, but I think it's called Special Purpose Diodes. I can't remember exactly what the book talks about. You'll run into these guys. This is the symbol for it. This is a device called a triac. I'll tell you what chapter it is. I was playing around with the PowerPoint this weekend, so it's chapter 11. But everybody okay with SCRs? Y'all know basically how these things work? Okay? And odds are you're going to get into some DC drives. You're going to run into those things. As soon as I can get this guy right here low, it keeps telling me. Triacs, diacs, and UJTs. The problem is they still teach UJTs, but UJTs are hard to find now because they will replace something called a PUT, which is a programmable unijunction. So these are different types of triacs. This is not in your book. I just drew this myself. This is basically the makeup of a triac. You have two SCRs. Over here, this is a standard SCR. Over here, notice it's reversed, and we have the gate hooked up to the N. Here we have the gate hooked up to a P. This is the makeup of a triac. This is not in your book. It's just, to me, this was a lot easier to see. Okay? So how do we turn this thing on? Well, this is an AC SCR. We use them in light dimmers. So if you got a light dimmer in your house, odds are it's using a triac. If you got a motion detector on your house that turns lights on, odds are it's using a triac. The street lights out here, when they come on at night, odds are they're using a triac. Because these guys, if you ever dealt with a solid state relay, AC relay, is probably what? It's probably a triac. So what we can do is so this guy here is always forward biased. One side is always forward biased. But we're going to put this guy on AC. So that means if this is positive, this will be negative. If this is negative, this will be positive. So the triac itself is always ready to be turned on if you put it on AC. We wouldn't put this on DC. So how do we turn it on? Well, we turn it on relative to MT1, or main terminal 1. Some people call this anode 1. Most of your spec sheets will call this main terminal 1 and main terminal 2, or they might call it anode 1 and anode 2, which is kind of misleading because it's the anode for this side and this will be the anode for this side, right? You understand? But notice, when this guy here's forward biased, which means I would put a what? Let me do it. This is one. So up here we have positive, we have negative. What would be required to turn that guy on? I can't turn this guy on because this guy right here is reverse bias, so it's off. Okay, so I'd have to put a what? A positive on the gate. This guy would turn on. Now, where I turn it on will depend on how much AC I get through, right? So I could take that the same circuit I did before, the exact same circuit. By the way, this resistor is in here just so I don't short circuit. And then we'd put a little capacitor right here. And then we'd come over and we'd put our load right up here. And then we would come in and put our triac right here. So as I draw it right. And then we would gate it right here. So what I do when I move this, I change the firing angle. So if I turned it wide open across my load, I'd be getting this. If I started cutting it off, I would start getting this, right? Y'all understand? I'm trying to draw a flat side, then it'd go flat, and then it would go over, so my light would get dimmer. That makes sense? So if you got a light dimmer, anybody got a light dimmer in their house? I guarantee you, if you tore that sucker apart, most of the time they seal them up in epoxy, but if you tore them apart, it's nothing but what? It's nothing but a triac. And this is the basic circuit that you're using right there. So here's that little old slider right here that you're sliding up and down, right? Or whatever you do, or the knob you turn. The older ones had knobs. A lot of the new ones now, you just use a little slider to dim your lights with. If you got a motion detector on your house, or if you got a light that comes on at night, it goes off during the day, which all these lights out here in the parking lot do that. Odds are it's got a little triac in there. Very simple circuit, by the way. I've got it hooked up here. Okay, but when this oops. Okay, but let's swap it around. So when this goes negative and this goes up, when this goes negative and this goes positive, then this guy right here is what? It's off. This negative would be here, this would positive be there. What do I need to put on the gate? Turn this guy here on. What polarity I need to put on this? Yeah, I got to put a negative over here. And then this guy right here would turn on. And then on, Rich. And then it would let the negative alternation through. Pretty neat little device. Oh, here's another little circuit I have set up right here. Here's a resistor. This is a, what's this guy right here? Here's my triac right here. Can y'all see what that is? Can't read it. Oh, let me change the name. So here's my transformer running all this stuff right here, by the way. Here we're using the center tap. We're only using half of it on this little light bulb. So I have a little light bulb right here. What's this right here? Photoresistor. You ever seen this circuit before? Oh, it's getting dark outside. Very simple little circuit. So what this would, that was turn the light on when? At the dark. Turn the light off during the day. Doesn't get hot at all because it's either what? On or off. Now these guys will get warm because they got two junctions in there. So you know that's going to be about 1.4 volts drop across there. And if you put a lot of current, like I said, 100 amps through a triac, that's still 140 watts, right? You understand that? So these guys will get hot. They'll be heat sinking. But if we tried to do it with any other, if we tried to do it with a rheostat, my rheostat would be as big as my house, right? You understand? Because those suckers are, when you drop 15 volts, they're going to drop 15 volts at 100 amps, and that's a lot of watts, right? So yeah, I could control my light. You could dim your lights, your incandescent lights. You could dim them with a big rheostat. But how big would it have to be to run a 100-watt light bulb? You understand? So a 100-watt light bulb requires about 1 amp to run a 100-watt light bulb. So very, very electronically, I can control it with this. If I tried to run this bulb with this little old tiny photocell, I would burn it up, right? You understand? But all this guy here is providing is gate current. So a very, very simple circuit. Now the problem is that so all I've got a resistor, 2.7K, and then I've got my photoresistor right here. Then I've got my light bulb right here. And then I've got my triac right here. And my gate is connected right there. Putting 6.3 volts AC right there. That's coming off my transformer. I'm taking it off my center tap. And this is all there is to that little circuit. We okay? Now, of course, when it turns on would be, so I could come up here and, of course, I'd put a fixed resistor. I could come over here and make that variable, and that way I could determine when it comes on, right? How dark it has to be. Very simple circuit. Normally, we gate this thing with a device called a diac. So that's next in your book. Especially if I'm going to do it on a light dimmer. The problem we have is getting an equal when it switches. Where does it switch at? Y'all understand what we're saying? So we have a device called a diac. A lot of people try to draw them like this, but they're not really like that. They try to give you an equivalent circuit like this. But this is not the way they work. A lot of people call them AC Zeners, but they're not AC Zeners. Because if this was an AC Zener, what would happen is it would come over here and it would break over and do this, and over here it would break over and do that, right? You understand that? These are what these guys do. So they come up here, and then when they break over, they do this. Their opposition drops down to almost zero. And then they'll come over here when they hit their breakover voltage. They break over and their opposition drops way down here. So what happens if I come over here and put that diac right here? For one reason, now we're going to be able to control when it breaks over, and it'll break over at the same, well, we'll fire it at the same voltage every time. So if we come over here and look at some triac firing circuits, odds are they're going to show some of those. They'll show a lot of diacs. By the way, this is another device. What's this a symbol for? It's right there. Optical coupler, so-called optical isolators. This is another way we can fire these things and isolate them. So here's the circuit. So here's a Here's a little circuit that we have, but instead of trying to fire it off that capacitor, what would happen, it would fire at different angles on both sides. But what we do is we put this diac right here, which breaks over, and when it breaks over, it puts a high energy pulse into the triac, and it'll fire it both directions at the same angle. So there it is again. So there's a diac. So here's a diac. Here's a triac. See, so most of the time, so this would be a light dimmer circuit right here. Except they're drawing the lamp real big. The lamp wouldn't be right there either way. The lamp would be over here. So whoever did this wouldn't. If you got a light that comes on at night, or a motion detector that only comes on at night, if you take that apart, I fixed them before, but now they're pretty cheap. Where the light would stay on all the time. If the light stays on all the time, usually it means that your triac is shorted. So, you know, if you can get in there and get the part number on it. If you don't even get the part number, you know, you can get the ratings on the thing, you know, 120 volts, so much current. If you're running, you know, a 100-watt bulb, you can pretty figure out what triac to put in there. So these guys here, you know, solid state devices, they can become leaky, but another thing that can happen is they can short, and your motion detectors and everything are outside, so they're in a pretty harsh environment out there. So I've seen them short, I've seen them open, and break them apart, and you see the triac and the diac in there. It's really neat. It's not much to it, and they're not real hard to fix. But now, you know, that's back when they used to cost a pretty good deal of money. So what does a triac do? Is a lot of people say it's an AC Zener, but that's not true, because if it was a Zener, once it broke over, it would maintain a constant output, right? When this guy here breaks over, just like an SCR, if you break an SCR over forward biased, it'll turn on. This guy, if you break it over forward biased, it will turn on. And how do you turn it off? Drop it below its holding current, right? Drop it below its holding current. Now on AC, it automatically do that. So if you break over a triac, it's going to do the same thing in the forward direction. It's going to conduct until you cut it off. So you need to make sure when you get these things that they have a forward breakover voltage, that's probably at least twice of what you're trying to block, right? You understand? And then make sure you get the right breakover voltage on your gates and stuff, and then of course the current rating of that. I don't know if we got any data sheets on triacs and diacs on our website. If it's not, I'll put some up there. So let's see, Zeners, voltage regulators, UJTs, BJTs, SCR. This is a little SCR. This is the one that I've got hooked up right here. So this is the actual SCR that I have hooked up right here. I don't remember which one these are. What does it say? So we got the 106B1. So it's what? A 4 amp? Undoubtedly, this must be a cross, guys, so I don't know which one it is. I'll have to look it up. Peak off-state current, maximum off-state voltage, gate trigger current, gate trigger voltage, total turn on. I don't see And this is to be the pin out, cathode anode gate. Okay, so here's our DC holding current right here. So if we drop this thing below 3 milliamps, and it's going to do what? Probably do what? Turn off. If we keep it above that, it's probably going to be what? On. And I don't have any triacs up here. I do have a UJT. So this is the symbol for a UJT. And there's a math formula. I don't know if it's in your book or not. But we set this thing on a little RC time constant. And then when it gets up to a certain voltage, then what it's going to do is it's going to fire, pop. And then what it does is discharges the capacitor, and then it turns off. And then what does it do? Wait for it to charge up again. These are oscillators. These guys right here will set up and generate oscillation, but they do a funny little thing. So if I hook this thing up right here and put it across DC, it would just set up there, and it would just keep firing by itself. So normally we use UJTs as oscillators. We use UJTs as firing circuits for SCRs. Never seen them use it to fire a triac. So here's where it covers diacs. This is where the book covers. This is the actual makeup. It's not very important. This right here is a pretty best diagram that I've ever seen. That's why I stuck it in there. The diac is exactly the same thing. In fact, it looks like an NPN transistor, right, without a gate lead. And this is not exactly true, because this is what it does. So what happens is when it fires, it drops way down. If it was actually a Zener, what would it do? It would go this way, right? Diacs and triacs may be used to control the brightness of a lamp. This circuit would be used to run we have a special motor called a universal motor. This is what we use in hand drills. This is what a lot of fans use. Universal motor is a motor that will run on AC or DC. Now we can run these guys on triacs. So they're a universal motor. They actually have a commutator. And so this is probably, these guys here create high torque. I think that's the way you spell torque. My brain went dead. You'll find these guys in hand drills. You'll find them in vacuum cleaners. Take a vacuum cleaner apart, it'll have a universal motor in it. These guys have very poor speed regulation, but they extremely high torque. So this is when you got like your drill, and it runs real fast until you put it into something. What does it do? It slows down. But what it's doing is when it slows down, it creates more torque. So it actually gets stronger the slower it runs. What's nice about this is we can change the voltage across here, and we can vary the speed very similar than we can with a DC motor. So a universal motor, we can control that with a triac. And so this is but it'll be a series motor. but they call them universal motors because all your current goes through the field, and it means so the field has a very low X of L, which means we can put AC on it, which is pretty neat. So I've seen them run. We use Tri-X to control our universal motors. We won't do it. We won't do a regular motor though. Okay, so this is the UJT. It's a really strange animal. So the way what it sets up is it sets up two resistors. So here they are right here. And in the center of them we have a gate. And here's the leads, B1, B2, and the emitter. And we fire it relative to this guy right here, which would be B1. So what we have is we have what they call the forward standoff ratio. And what it is, it's the ratio of these two resistors right here. So it's going to be, I think it's R1 over R1 plus R2. I think that's the formula. I'd have to go back and look. Is it in there, the UJT? But this is given in the formula sheet as the intrinsic standoff ratio. I think is what we call it. And what you do is that where this thing fires, where it fires at is you come up here and you take whatever you apply. So let's say we put 12 volts, and the intrinsic standoff ratio is 0.3. Well, what I would do is I could calculate this voltage. I would take what? 12, and I'd multiply it by 0.3, and what would that give me? Huh? Okay. 3.6. So that means when we got this thing up to 4.1 volts, this guy here would fire. No, it's not 4.1, Rich. Can't do math. Uh, 4.3 volts. So what it is it takes this. So this is a PN junction. What do we have to turn this thing on? So over here I would have 3.6 volts. So I would have to make this 0.7 of a volt more positive. Y'all understand that? And then this guy here would turn on. When it turns on, this guy here drops down to pretty close to 0 ohms. So what we would do is we would come over here and we would put a resistor capacitor network. And then what would happen is when this guy here charged up to 4.6 ohms, then this guy would turn on, this resistance drops down to 0, it would discharge the capacitor, then the UJT turns off, and then the capacitor would start doing what? Charging up again. When it got up to 4.3 volts, it would do what? It would fire, discharge the capacitor, the UJT would turn off, and it would start charging up again. So if I was looking across my load, if I had it down here, then what we would do is we would get a signal that looks like this. And We set that with this ratio of this resistor and this capacitor. So we use these guys for oscillators. What's oscillator? You know what oscillator does? Have y'all heard that term before? What does it do? I mean, so what's an oscillator do? If you heard the term before, you're one of those that go like this, and if you don't know what people's talking about. I see that all the time. People don't want to think people don't think people, a lot of people, most people don't want other people to think that they don't know what they're talking about, right? So, what does an oscillator do? Anybody know? Take a guess. Sort of, but technically an oscillator is a device that takes DC and converts it back into a pulse stream. A lot of people says it takes steady state DC, and we can use them to convert it into AC too. So, well, like these boxes that you buy, you know, that you put you take it and plug it into your battery, and then over here you get AC. That's an oscillator. Most people call them inverters, but that's all it is. It's just an electronic circuit in there that oscillates, and it's set up to oscillate at 60 hertz. So you can take devices that are designed around 60 hertz and run them off your car, which is pretty neat. My wife's van's got one built into it. It's actually got a 120 volt plug in the car, in the van, that you can plug stuff up with, which is pretty neat. But you can buy these. You can buy them at AutoZone or any place like that, these inverters. You know, that's basically what they are, oscillators. Now, they don't use UJTs because this wouldn't be a pretty enough signal to run an AC device on, but it's the same principle. So what we do is we take it's a device that takes steady state DC and converts it over to AC. In this situation, it would be a pulsating DC. And what we would do to set the frequency of oscillation, it would be this size of this resistor right here, a resistor and a capacitor. And it probably has the formula somewhere. So if we look at our data sheets, that's what we'd be looking at. We'd be looking for so here's a UJT. So there's the symbols. So since this is the error, they refer to this as E. What do you think that stands for? Emitter. And then B1 and B2. And let's see, storage base inter. I don't see what I'm looking for, guys. That right there don't show very much. This is all that's there. This one don't show the intrinsic standoff ratio that I was looking for. See if I can find another. But normally what we'll do is they use this to fire. They use this a lot to fire an SCR, which is pretty neat. So guys, I believe that's about all we're going to talk about this semester. And the book does a pretty good job on this too. Triax, Diax, and then so that would be the output of this circuit right here. Oh, this is a Triax firing circuit. It would show any SCR firing circuits. So the book has a Few more chapters, covers a little bit about the digital circuits. I think it's got a chapter in there on what's the rest of the chapters. Like I said, I don't know how I did what I did with my book. So we got a lot of symbols y'all have to learn, right? But that's the name of the trade. Have any of y'all, did any of y'all take the blueprint reading class? There's more symbols in that. There's a lot more symbols in there than it is in here. That's for sure. What's that? The triac has the gate lead. The diac is just a device that breaks over when it gets up to a certain voltage. So the diac has exactly the same symbol, but what's missing? There's no gate lead. And I can't even think of the names of the two sides because I don't know what they would call them because there's no polarity on this thing. You can put this sucker in a circuit anyway, but it's designed to go into an AC circuit. What they call the leads, I don't even think your book gives you the leads, but this is one of those guys that don't need a lead identified because why? Because it goes in the circuit either way. I mean, it's an AC circuit. It breaks over the same voltage no matter how you put it in there. Now, the triac makes a difference. So MT1 is on the same side. Main terminal 1 is on the same side as the gate symbol. So this is MT1 and MT2. So when we talk about how we bias this thing on, we bias it relative to MT1. So if MT1 is negative, then the gate has to be positive. If MT1 is positive, then the gate has got to be negative. So it's got to be opposite, right? Y'all understand that? This guy is used in solid state relay, AC relays. These guys are used in light dimmers. These guys are used in speed control for universal motors. These guys are used in automatic light systems, right? You understand, that comes on at night. So these guys are used all over the place. But the problem is that their turn on in one direction is not exactly the same as their turn on in another direction. So what they do to make it turn on at the same voltage is they put a diac in series with the gate. So when the diac breaks over, we don't get a slope, we get a nice big energy pulse that goes into the triac and fires that thing at exactly the same point all the time. So very seldom you'll see like the little circuit that I've got up here, which works out real great because all it's doing is running a light bulb. It's a cute little circuit. And we run into these guys here all the time, right? Very simple circuit to build. Real simple. So if you wanted anything to be active at night and not active during the day, then this little circuit right here would be really, really easy to do. Nothing but a photocell and a resistor. And then of course, so this guy's, and then when it gets dark, what does it do? And then when it gets light, it turns off. Very simple circuit. And the triac doesn't really get hot because it's either what? It's either off or on. I could do the same thing with a bipolar transistor, but the bipolar transistor would be in the active region. When it's in the active region, it's dropping a voltage. And when it drops a voltage and you put a current through a voltage, P is equal to what? V times I, right? So that way, bipolar transistors are great, but when we operate in that active region, we're going to have to sync them a lot. So that means you go out and take your radio apart and you look at those outputs, they're going to be up against a heat sink, right? You understand? Because they're operating in the active region. And if they operate in an active region, they're going to drop a voltage. If you push a current through a voltage, you get what? You get heat. So So these guys are used a lot for switches. We got some solid state relays in there. Very, very popular, no mechanical parts to them. Regular relays have, they're electromechanical devices. So electromechanical devices, you got two things that can fail. It's like your car, right? We talked about that. You got two things on your car that can fail. It can fail mechanically, or it can fail what? It could fail electrically. Oh, by the way, PLCs use these guys here too. If you got an AC output module on a PLC, it's got tracking. That's what it fires the output with. It fires it with a track. If you got a DC output module, it's going to use a transistor, but on a PLC, a DC output module, the transistor is either saturated or it's off, so they're using it like a switch, right? You understand? So transistors work great if we can, we don't have to heat sink them as much if we operate them as a switch, because they're either what? They're either on or off. It's when we get those transistors in that active region that starts giving us problems. Okay, any more questions? I'll see the symbols. So on test 4 there's going to be a lot of what? Symbols. And that's the name of the game. If you don't understand the symbols, then you don't even understand the name. So that means if you knew the symbol for a track, but you couldn't understand, for a track, and you didn't quite understand how it worked, then you could look it up now because you know the name. If you don't know the name of the signal, you can't go to the internet and say, I'm looking up one of these things, right? These thingamajigs. There's no telling what you'd get. So just being able to identify the symbol and knowing the name, I know there's a lot of information, but just knowing the name of the symbol gives you the ability now to do what? Look it up. And man, you can look up all kind of stuff on triacs, triac operation. Just type that sucker in and you'll get all kind of people that's going to tell you how a triac works. So just knowing the symbols are very, very important. Okay, any more questions? So what we're doing on our labs. So we did a class lab. We did 2 class labs last class. We did one for the common collector, right? And we did the push-pull amplifier or the complementary amplifier. And Chase, those have been recorded and uploaded, so you need to get that and turn that in. And what am I looking for? Let's look at our labs and see what we can do. See how many we like. We might do some of these in class because we can do them in class a lot faster than y'all can do them yourself. So labs.